The airbrush has been around for thousands of years, even tracing back to the Paleolithic era where people painted hand stencils on cave walls by blowing paint through hollow bones. As you blow through the horizontal bone, the pressure above the vertical bone decreases, allowing for the paint to be siphoned upwards and blown onto the wall. This tool is an ancient example of a mouth atomizer. While ancient airbrushes are very different from modern airbrushes, Bernoulli's principle is at the center of both mechanisms. Let's look at an example with a basic mouth atomizer using straws.
In our simplified setup, one straw is in a cup of water submerged about halfway. A second straw is used to blow air over the top of the straw in the water. There is an increase in the velocity of the air over the top of the submerged straw, and there is a decrease in the air pressure at this point. The decrease in pressure causes the water to rise up and is then sprayed in the direction of the blown air.
Modern airbrushes come in two types, gravity feed or siphon feed. In each type of airbrush, the main body of the airbrush has a nozzle where the paint is sprayed out, a paint reservoir, a trigger to release the paint, a needle to break the paint into small particles in a process called atomization, and a nozzle that connects the airbrush to an air compressor. The siphon feed airbrush relies on blowing air over the paint chamber in order to siphon the paint upwards and then out of the nozzle. We're interested in the fluid mechanics behind a siphon feed airbrush, and we want to determine the velocity of the paint coming out of it.
Using the Bernoulli equation, we can establish a link between different variables like velocity and pressure. To simplify the Bernoulli equation, we must assume that the flow is frictionless, inviscid, irrotational, and there is no shaft work. We also have an incompressible flow. This means the density of the fluid is constant, and pressure variation is very small compared to absolute pressure. The Bernoulli equation is derived from the principles of conservation of energy and conservation of momentum. We can equate the energy of the fluid coming into the airbrush to the energy of the fluid as it leaves the airbrush. When the airbrush is held horizontally at a constant height, the potential energy is zero and the term goes away. We can rearrange our equation and solve for the velocity of the outgoing fluid. From our mass balance equation, when we have a constant pressure from the air compressor, the mass flow rate should be constant. Since the density of our paint is constant, when we increase the diameter, the variable that must decrease is velocity. Apart from the airbrush, Bernoulli's principle has many other applications as well. Bernoulli can even be used to find the lift force on an airplane wing or velocity of smoke leaving a chimney. Can you think of ways Bernoulli's equation applies to the world around you? Let us know in the comments. Thanks for watching.